as you can see from the theme, we are at a beef ranch. That's why this slide is themed, and it's an animal farm. Anyway, welcome to the workshop, Zero to Hero, smart contract. If you have any questions, please feel free to interrupt me at any point. And we'll now begin. We got 30 minutes. We good? We good? Yay! Hooray! So this is kind of the agenda we have today. We'll talk a little bit about Mantle, which is sponsoring me to be here. A little bit of what is the EVM, the current state of developer tools, your Foundry, Hardhat, Truffle, ApeWorks, the various smart contract programming languages. And if time permits, we can check out more advanced topics and/or tooling such as fuzzing or proxy contracts. Can you guys hear me? Yes. Good. Great. Perfect. So who am I? I am libEVM. These are my socials. I am currently a developer relations at Mantle. If you would like to talk more about Mantle, feel free to just come and ask me questions after the talk. But I'm an engineer at heart. So what is Mantle? I don't want to show too much, but the TLDR, it's an EVM compatible scaling stack for Ethereum. So we're trying to bring the good parts of Ethereum and make it better. So why EVM compatible? We would like to leverage existing tooling and the community, and we want to build on the shoulders of giants. So we want to be able to use the existing infrastructure like MetaMask. We want to be able to use the existing tooling like Truffle, Hardhat, Foundry, the existing programming languages like Solidity, Viper, Yule, Huff, and we don't want to keep reinventing the wheel. We want to be able to absorb the existing community. And also a lot of these things take a lot of time and effort, and we thought it would be better to just inherit them rather than compete against them. So build with them instead of against them. So these days there's 3 standard toolings out there. If you would like to get started with smart contract development, the recommended one is Foundry from Paradigm. And if you like JavaScript, I would recommend Hardhat. But if you like the Python syntax, I would recommend ApeWorks. Now, Foundry is a little bit more new. It's written in Rust, so things are a lot more quicker. Whereas Hardhat is a lot more familiar for those of you who have been in the JavaScript ecosystem. However, you have to write JavaScript to test your contracts. Foundry, you can just test them in Solidity. Whereas ApeWorks and Hardhat, you have to write the various languages such as Python or JavaScript to test the logic of your smart contracts, which might not be ideal as there's a lot of context switching between them. And we'll go a little bit overview about the smart contract languages. We have the most widely used today, Solidity, which I'll be checking it out. I'll be going through a very brief overview on things. If you are an optimizer who likes to gas golf or who really likes to get close to the bare metal, Huff is a good alternative. If you like the Python syntax or if you do a lot of math-heavy operations, Viper will be the recommended choice, such as Curve. However, do be warned that it is not very extensible because due to limited language support. Huff is also not recommended to be used in production, actually, simply because it is very hard to get audited, and it's very hard to find the logic. It's very hard to visualize the logic control flows. But at the end of the day, they all compile down to EVM bytecode, so it doesn't really matter as they are just a form of abstraction. And with that being said, let's check out a live demo. So in the live demo, we'll be going through a couple of topics, mainly the keywords in the smart contracts, as well as how to deploy your own ERC20 token. So right now, I'm using Foundry. So can you guys see the screen? Is it zoomed in enough? Perfect. So usually how this would work is that you would start your repository with Forge init. However, because the internet is quite limited here today, I decided to just go ahead and initialize everything in case the internet isn't too kind with me. Just need some water, 1 second. So in the Solidity programming languages, there's a lot of primitives. One of the primitives is a uint256. And if you guys are curious what that means, it just means I can store a really big number that is 256 bits long. Unsigned, meaning it goes from 0 to 256 bits. It doesn't account for negatives. If you were to do int 256, it'll be a negative number. You can go from negative to positive, but your range will be halved. So these are there's special keywords such as uint256, and you can also make this number public, meaning this number is accessible externally, or you can, and behind the scenes, I'll show you what actually happens behind the scenes in the Solidity programming language. Keep in mind this only happens in Solidity version, I think 0.4 and above, so not all versions of Solidity will have this, but if you're using modern tooling, it should have it by default. So the public keyword makes your number public, but what it does behind the scenes is that it actually creates a new function called number, get number, because we can't have a collision in keywords, which returns uint256, and that just returns the number. So behind the scenes, if you type out public, this is what it actually does. Now, but since we already have this public keyword, we don't have to recreate this function. We'll just make it a lot more convenient. Cool. We can also mutate the number. Like these variables are mutatable by default for those of you guys who are coming from the JavaScript world. This should be very familiar. You can call .setNumber, and you can override the number that is currently being stored in this contract. So this contract counter has a couple examples. You have a setter, and you can increment the number. And let's see how we can test it out. So this is Foundry, by the way. When you initialize it, I just realized I didn't went through it. It would set up a couple folders. You have the test folder, the source folder, the script folder, and a library. The library is where all the library is where you import existing contracts, such as OpenZeppelin, ERC20, where you can immediately create an ERC20 token, which we'll be doing later on today. Foundry also has this really cool thing called scripts, where you can write scripts in Solidity, which is actually not supported anywhere else outside of Foundry. This is very useful when you're testing Solidity contracts because you don't have to keep context switching from one code to another. However, this tool is also Foundry specific, so you have to use the Foundry tooling in order for you to use it. But we probably won't dive into this category today. So let's see how we can interact with this script. And usually you would interact with it in the tests folder. So we have this contract called counter test, which is going to test our counter object. So again, this counter object, all it does is that it has a number. You can store the number, you can read the number, and you can increment the number. And so how we would do this in counter test is that we define our counter object, we create a new counter, we initialize the counter to be 0, which is in the setup process. So think of this as a function that you run before every time you initialize the contract. And we'll test the increment of the number, and we'll test setting the number. So if we increment it from 0 to 1, the number in the counter should be equal to 1. So that assertion should be true by default. Or we can also test setting the number to some arbitrary value x, of which the Foundry framework will automatically fuzz this for us, meaning it will test various numbers from between 0 to 2 quadrillion, whatever the maximum number is in 256 bits, and we will make sure that that assertion, that the number is equal to x. And so we can run forge test to test this out. We compile the project, And now both tests pass. So increment, we have successfully tested increment, and we have successfully tested the number. So that's how you would set, let me drag this back. That's how you would test smart contracts in Solidity. Now Solidity and most smart contract programming languages have a special keyword, and we'll be going through some of those special keywords with you today, such as function get keywords, public. We have these things called message.sender, tx.origin, block.number, and block.timestamp. So these are smart contract specific things, which I'll go through in a second, which you won't be finding anywhere else other than Ethereum or any Ethereum-like language, Ethereum-like environment. So cool. Let's check out the difference between message.sender and tx.origin. So let's get message.sender, return message.sender. They're both addresses, if you're wondering. And what message.sender implies is that it's asking, hey, who called this function? So who called the get message sender function? Whereas tx.origin also returns an address. I assume everyone here is familiar with addresses a little bit. All right, cool. And we can return tx.origin. And so what the difference between tx.origin and message sender is that tx.origin returns the originator of the transaction, whereas message.sender returns the address of whoever who called the contract. And we'll make this a little bit more concrete. Let's run some test keywords. Let's make this a function called test keywords, and we can actually log stuff out in Foundry with the log address keyword. But you have to inherit from the test functionality again. This setup should be default when you initialize your Foundry project. So we can try and log an address, for example, message.sender, and just make sure that this works, forge test. But since this test will pass and we want it to be extremely verbose, we would give it 3 V's, test-vvv, which means very, very verbose in my opinion. I'm sure Georgios will disagree. And as we can see, we have logged out an address here. And if I remember correctly, I can log out a string with the address, message.sender, counter test. Nope. Should I dive into it? Yes, we have a lot of time. Might as well. Maybe not. It's ds test. All right, it's okay. I'll just log a string. Message.sender, counter test. And that's the message sender for counter.test. But if we emit the address for counter.get message sender, it would actually be different. Counter object. As you can see, even though we're both getting message.sender in the test file is different from the message.sender in the counter file. And the reason why is because the counter test file is actually calling the counter contract. So in theory, if I logged out the address of this contract, which is the counter test, it would be the same as the message sender for the counter object when we call get message sender. And let's test it out. Address of counter test. And as we can see, the address of the counter test is 0xfa something something, which is also the message.sender for the counter object Again, this is because the counter test file is calling counter.getMessageSender, and that is why the two addresses are the same. However, if we check the tx.origin of counter, it will be the same as the message.sender as the counter test. And let's check that out. Tx.origin, counter, get tx.origin, whoop, and boom. Tx.origin is the same as the message.sender from the counter, and that is because the originator of this whole transaction actually created and calls counter test, which is the tx.origin. So that is the message.sender for counter test, and which is in fact the tx.origin for every instance. So if we get the tx.origin of this contract, it will be the same as everything else. And we can test it out. So yeah, those are like some of the keywords you can find in Solidity. Just keep in mind like these, the little nuances between message.sender and tx.origin. Now, a little hack that a lot of smart contract developers use to ensure that the sender of the transaction is a human, and by human I mean an EOA or externally owned account, meaning it's not a smart contract account, that oftentimes they would put in this keyword, this requirement where the tx.origin is equal to the message sender, which just basically means that your contract, the caller, can't be a smart contract, and that way you can't perform botting actions. For example, determine a number that your contract is going to predict in the future, because you can get all the data from the smart contract. Anyway, this is how a lot of smart contracts make sure that the caller of the user of their application is not a bot, if you're wondering. Now we also have some keywords such as block.hash, which just returns the hash of the block, and that returns you a bytes32, which is in fact just a UN256 packaged nicely. Block.hash, and we can check this out, log bytes32. Hash, block hash, is it a function these days? I don't remember. Oh, block hash, block.number. Yes, that's how you get it. Cool. And it's 0 because we're in a test environment, so we haven't initialized anything. So that's how you get the hash of the current block. And if you would like to get the block number, you can log UN256. UN log UN. And you can log out the block number, which is 1. So those are like some application-specific keywords in Solidity. Cool. All right. What else? We got 10 minutes. Let's try and make our own token here, our own ERC20, and it will be extremely simple. All we do is import from the Open Zeppelin contracts /token/ERC20/ERC20.sol. And now if we just do this, my token is ERC20, give it a name, super token, and then just name it super, and delete everything else, and you have just created yourself an ERC20 token that fits all the specifications. Very, very cool, very, very easy. Let's try and test this. I'll just keep this here a little bit longer so you guys can see how easy it is to make a simple token. Okay, great, our audience size just doubled. Hooray, welcome. So this is how you make a super simple token, and we can now test it. Because we renamed it to my token, we have to change it here to my token public, counter it, but we'll just call it token. And we'll set up a new token, and this is how you make a new token. Very easy, you just inherit from all the standard ERC20 contracts. Oh, great. Our audience size just quadrupled. Amazing. Thank you. Yes, you missed the best part, which is the cow-themed slides, because we are in a beef ranch. So everything's animal themed. But, yes, it is very cute. But we're almost done. I think we got like 9 more minutes. But anyway, this is the token. You can make a new token, and you can test the functionality of the token. Test token, public. And again, this token inherits from it fits the ERC20 specifications. So if you want anything like, let's see if the internet works. Okay, so what that means is that it fits the ERC20 token standard. You have all these functions. It has the name, it has the symbol. Let me see, can you guys see it? Yes. It has decimals, it has total supply, blah, 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 bounce off, transfer. These are mutable functions, by the way, that mutate state. Transfer form, it's just from inheriting from this ERC20 contract. And we can check it out right now. Emit log string, token.name. And notice that I didn't define anything in here. Everything is inherited from the ERC20 contract. This is, in fact, in my opinion, very lame, because I'm not a big fan of object-oriented programming languages, but here we are. But these are the tools we have. Okay, great. We'll log out the name of the contract, super token, and as you can see, we never define the function name, but we can still call it. We also have stuff like symbol, which is just super, as we have defined here. But there's no way to mint any token right now. So we need to actually create a function, owner mint, or like there's a magic mint, which takes an address, A, and then mints some amount B, 256B, to some user. And there's actually an internal function called mint, where you can mint the mint the tokens to address A with amount B. And so, for example, right now, my token, I don't have any token. It should return as 0. But if I mint myself some tokens, for example, token.mint, address this, I'll mint myself 100 tokens. Now the E18 is just saying that I want to put this to, I want to give it 18 decimals. That's just the standard. A lot of token standards, a lot of tokens such as DAI, wrap ethers all use 18 decimals to represent decimals. Don't ask me why it's 18. I have no idea. But we should have 100 tokens in our balance right now. Oh, it's magic mint. Yep, magic mint. And yes, now we have 100 E18 tokens just from inheriting a contract and creating a fancy function called magic mint. We have now created a token that is mintable for anyone, which I do not recommend. So generally, what happens is that you would put a require where the message.sender is some address, for example, 0x42, and if it doesn't pass, then this whole function reverts, and we can check it out in this case. It just reverts, so you have like a owner gated mint function. So I think, yeah, that's how you make a token in ERC20 land, and I just realized that we're running out of time. We're running out of time, and I would have loved to dive deeper into more advanced toolings, such as Slither and fuzzing and proxy contracts, but I will give the next speaker 5 minutes to prepare, and thanks and Q&A, and happy deployment to your smart contracts. Those are my socials. If you want to check it out, please do check out mantle.xyz. We have a lot of grants, prizes to support anyone who wants to deploy on our network. We are a layer 2, optimistic layer 2 that is EVM compatible. Again, lots of grants. So thanks, and if you have any questions, feel free to chase after me after this talk. Thank you very much.